I remember when I was first learning about the function, the role that the gradient plays in geometry and describing tangent planes and things, and it was really quite difficult for me to wrap my head around. So I think I'm prepared to have a lot of sympathy for people that are having a hard time with this topic. But in retrospect, when I think hard about all the mistakes that I made, a lot of them were mistakes of language. So I'm going to try to remember all those mistakes that I made back in the year 2000 or so when I was learning about multivariable calculus for the first time. And I'm going to see if I can clear them up. And my favorite mode of trying to clear things up is to write complete sentences. And sometimes they end up being quite long because I'm trying to take care of all the details. So here in section 14.6, number 1, I'm given this function x squared plus y squared plus z squared, and actually I'm giving it in the form of x squared plus y squared plus z squared is equal to 3, an algebraic equation. And I remember back when I was learning this stuff that it was really hard for me to know whether my textbook was telling me about a function or telling me about an algebraic equation, or whether the two things were the same or different. Everything was very murky to me. And so you've probably noticed that I try to keep those things very separate, right? Think about functions and equations as very separate things. It's nice because then you'll keep your solution sets, a property of algebraic equations, separate from graphs and domains and ranges, all these properties of functions. So I aim to use language here that very specifically makes reference to functions. In particular, functions are the things that have gradients. So we should never say, calculate the gradient of an equation, for instance, right? No. Functions are the things which have derivatives. So now, I want to make reference to a function, first of all. So I start like this. Since the gradient of any function is normal to the level sets of that function. Okay, so that is the reasoning that I'll be using here to come up with an equation whose solution set is a tangent plane to something. I want to think of the tangent plane to the level set of a particular function corresponding to something. So let's take a look at what I wrote next. The plane tangent to the level set of the function of three variables, x squared plus y squared plus z squared. I wrote out the function of three variables because we covered even in the midterm that when you have either an algebraic expression that stands for a function or an equation, it's not quite clear unless you say explicitly how many variables you have. So if I simply wrote x squared, I might have in mind the function f such that f of x and y is equal to x squared, and this thing does not change with y. So if I'm going to write down this and say that it specifies a function, well, that could actually be a function of 4 variables, and plus w squared could, let's see, it could be plus 0 times w, and then 0 y right 0 times w. So I explicitly said this is a function of 3 variables. See, this way I know how many components there's going to be in the gradient. Okay. So the plane tangent to the level set of the function of 3 variables, this is the function of 3 variables, a nickname for it, corresponding to 3. That is the set of ordered triples x, y, z, such that x squared plus y squared plus z squared is equal to 3, the equation that I found in the textbook, at the point 1, 1, 1. So there are lots of points in that level set besides 1, 1, 1. For instance, square root of 3 is 0, 0. Square root of 3 here. 0 and for y there, 0 for z there, that would give 3. So square root of 3, 0, 0 is another point in that level set, but I am only interested at 1 point, 1, 1, 1, because that is what the textbook is looking for. So really the textbook is saying find an equation that describes the tangent plane to the function x the tangent plane to the level set of the function x squared plus y squared plus z squared at the point 1, 1, 1. And of course you put 1, 1, 1 in there, you get 1 squared plus 1 squared plus 1 squared. Okay. So using this, right, how we get the normal to a level set has normal vector the gradient of the function evaluated at 1, 1, 1. And so next I calculate the gradient of the function 2x, 2y, 2z, and evaluate that at 1, 1, 1, which gives me 2, 2, 2. Okay, the plane is therefore the solution set to normal vector dotted with x, y, z is normal vector dotted with a particular point on the plane, right? So 1, 1, 1 is a point on the plane, and 2, 2, 2 is a normal vector. So a point x, y, z is on the plane if n dot that, but the position vector of that point is equal to n dot the position vector of a particular point on the plane. So then I take this algebraic equation and I simplify it to this form that doesn't involve any vectors. And I hope that that explanation helped to clear things up. If not, maybe watch more videos and make more practice for yourself.